let me go from mathematics back to physics. And I want to talk about a general concept in physics called field theory. So the idea here is that whenever we're doing theoretical physics, we have to decide, what type of objects are we making a theory about? Right? What are the fundamental ingredients in the theory? Now, in the cases that we've talked about so far this semester, the fundamental objects are either magnetic spins or they are molecules that are flying around in a gas or a liquid. And both of these are what we might call particles, right? So particles are objects with just a few degrees of freedom, right? And so the magnetic spin has a degree of freedom that it can point up or it can point down. There are two possible states, right? Or the molecules in the gas or liquid, each molecule has a momentum in 3 dimensions and a position in 3 dimensions. So 6 degrees of freedom per molecule. So this is one way of setting up physical theories, right? It's one way of thinking about the world, to say that the world is made out of particles and each particle has some small number of degrees of freedom. But there's a different starting point also. And the alternative starting point is this idea of fields. So the word field means a function of position or a function of position in time. And we can suppose that the world is made up of lots of fields, lots of functions of position or position in time, which are defined everywhere. And so at every single point in space, they have some degrees of freedom. So it's an infinite number of degrees of freedom when you consider the infinite number of points in space. Okay, so let me connect up the whiteboard to start giving you some examples of this. Here we go. Okay, so the idea for field theory, whoops, it's not shared yet. Is it shared? Do you guys see a screen yet? No, I didn't see it. That's weird. Oh, there it is. Okay, you guys see it now? Excellent. So the idea in field theory is, that the world is made of some fields, some functions of position or functions of position in time. And so the first example that physics students usually learn about is the electric field. So there's some E, a vector, which is defined for every position and time, right? Or a related example is the magnetic field. So a different vector as a function of position and time. So these are good examples. And so if you majored in physics, you learned, for example, Maxwell's equations, which say, how do these fields change as functions of position and time? And so the theory of electricity and magnetism is about describing the world made up of these kinds of fields. Now, there are other sorts of examples, right? There are examples in mechanics, right? So, for example, we could think about the height of a guitar string. If we want guitar string, it's stretched between two different points. And if we pull on it, it curves upwards like that, okay? And so it could be described by some height y as a function of x and t, okay? So that's another kind of a field with one spatial dimension, x, and one time dimension. Or we could say, similarly, what's the height of a drum head? This is harder to draw, right? But if you have a drum, right, the surface of the drum has some height as a function of x and y and time, right? And so there's a z of x, y, and t. Okay, and when you hit the drum, the height goes up and down, right? And it goes up and down in some complicated way that depends on the shape of the drum. And that's what makes the sound. Then there could be other sorts of examples, say in fluid dynamics. In fluid dynamics, we think of what's happening inside a fluid. And inside the fluid, there is perhaps a density that varies as a function of position and time. So rho of RT, and a pressure P of position and time, and a velocity field. So that would be a vector V as a function of position and time. The velocity field is one nice example to think about, right? Because you could say, if you have water in a pipe, right? So here's a pipe and water is flowing through the pipe. So it has some maximum velocity in the middle and a very small velocity close to the surface. Now, this velocity inside the pipe, okay, that doesn't mean that all the water molecules at this position are moving with that velocity. That is certainly not true, right? The water molecules are moving around in all different directions everywhere, but this velocity is some local average of what they're doing, right? So if you look right at the surface of the pipe, there are about equal numbers of water molecules moving in different directions. So the average velocity is 0. But if you look in the middle of the pipe, there's still water molecules moving in lots of different directions, but more of them are moving along the pipe and fewer are moving in the opposite direction. So there's some statistical average velocity, which depends on position. And that's what's described by this velocity field. All right. Now, what about in statistical mechanics? Okay, so for the kinds of systems that I'm talking about in this semester. Okay, so in statistical mechanics, we have the idea of an order parameter field. So that is to say, there's an order parameter which is not the same everywhere. Right? And so we've talked about other order parameters this semester, like the magnetizing magnet, or the density or volume per particle in a liquid or gas. And now I want to consider the case where those things might depend on position, or they might depend on position and time, so that we could get a magnetization, a magnetic order parameter that depends on position and time. Or we might get a density or volume per particle that depends on position and time. And that's the kind of thing that I want to talk about today and next class, and that's what's in chapter 6 of the textbook. Okay, so here is one example that is meant to be a kind of cartoon of an order parameter that depends on position. Okay, so here the idea is that I have an Ising magnet. Let's see, whoops. So here is the, okay, can I write at the top? All right, an Ising magnet. And so there are lots of little squares, right, representing the magnetic moment on lots of spins here. And it is encoded so that a blue pixel in this picture means the spin is down. And a yellow pixel in this picture means that the spin is up. Okay. And you can see that there are a lot of spins up and there are a lot of spins down. But something is changing when you go from the left side of the picture over here to the right side over there. Right? On the left side, you can see that it's mostly blue with just a little bit of yellow. And on the right side, you can see it's mostly yellow with just a little bit of blue. And so as we go from one side to the other, it changes. The fraction blue changes and the fraction yellow changes. And as a result, the magnetic order parameter, which is the fraction yellow minus the fraction blue, right? The fraction up minus the fraction down, that changes as a function of x. So if we look at any particular position, you know, a spot there or anywhere, that's just yellow or blue. But if we look at any, you know, little average region, there's some percentage blue and some percentage yellow. And then if we look at some other average region, there's another percentage and another percentage and another percentage. Okay? And so we could calculate the magnetic order parameter that goes along with any particular local region and make a plot of that as a function of x. And that plot would look something like this, okay? That way over on the left side, you have almost all down and just a little bit up, so that the magnetic order parameter is starting close to -1. Right? And then as we continue to move over and we do local averages at different positions, we are gradually going to see a bigger magnetic order parameter. So it becomes less negative, and then it's about 0 in the middle, where there's about equal amounts of blue and yellow. And then it becomes blue if we look at it over there. So if we do this kind of local averaging, we can see a trend of the magnetic order parameter going from negative to positive across the size of the system. This, we can regard this process as a local averaging. And the word that physicists often use for that is a coarse graining. Coarse graining. So coarse graining, it means zooming out, like on Google Maps, right? That you don't look up close at a small region. You don't zoom in at a small region and say, oh, this pixel is yellow, this pixel is blue, and so forth, right? But instead, you zoom out so that you are naturally averaging over some region, and you get an effective shade of gray, or whatever is on the scale between blue and yellow, right? You get an effective magnetic order parameter that describes a zoomed out region over there or there or there. It's a lot like an old-fashioned newspaper, right? I mean, you guys maybe have never seen a newspaper, but probably your grandparents used to read them, right? And in old newspapers, right, the photographs were just a bunch of dots that were, black on a white background, right? And if you look up close, you couldn't see anything, right? But if you zoom out, right, if you hold it away from your eyes, then your eyes would naturally average over the black and white regions, and then you'd see a shade of gray, and then the shades of gray would make a picture in the newspaper. All right. Now, if I talk about local averaging, you might naturally ask the question, what size should the local averaging region be? Should you be averaging over a little region like this, or a bigger region, or a bigger region, or a huge region, right? How do you choose there? There are basically two criteria for that, for the size of the local averaging region. One is that it must be much bigger than the size of an individual particle, so that there are many particles in each local averaging region. And the other requirement is that it must be much smaller than the length scale over which the physical properties change. So in the cartoon here, right, the individual particles, are like this size. Okay, so our averaging region must be a lot bigger than that. Okay, and we know that the magnetic order is changing from -1 over here to 1 over there. And it's changing roughly linearly. So maybe it changes by 0.1 over a size like this, by 0.2 over a size like that, approximately, okay? And so I don't have a specific size in centimeters here over which things are changing, but to get a significant change of the magnetization on a scale from -1 to 1, maybe you need to change it by 0.2. And so 10% of the overall change. And that happens on a scale something like this. And so the averaging region has to be much smaller than that. Okay, so we can ask, is it possible to find some local averaging region that satisfies both of these requirements? Is that possible? And the physical answer is usually yes. It is usually possible because in a typical physical system, the length scale of individual particles is usually something like 1 nanometer. Okay? That's a typical size of atoms or molecules or magnetic spins in a crystal. And the length scale over which physical properties change, that's typically something like a micron. So that would be the size of a biological cell or a typical liquid crystal cell or the wavelength of visible light. And typically, there's a lot of room in between these two length scales, between a nanometer and a micron, so that there could be some effective averaging scale that is 10 nanometers, 100 nanometers, somewhere in between those two limits. And so this idea of field theory works as a good physical approximation as long as that's possible, right? As long as there's a big difference between these two kinds of length scales. And in those situations, we don't even really need to talk about the averaging length scale very much, right? And so in most cases, we can just say, what's the average magnetic order parameter over here versus over there? And it's not even really necessary to define specifically what's the averaging length scale. So it's something that people have to worry about, for some kinds of computational research, if they're doing simulations and they're explicitly doing that averaging. But for other kinds of theoretical work or experimental work, usually it just comes out pretty naturally, and you don't need to specifically state what's the averaging region. It just works because this length scale is way smaller than this length scale, right? Because molecules are very, very small. Okay, So that's the general concept that I want to talk about, okay? Questions about the general concept, I'll invite that before I go on. Vijaya, are you raising your hand there? Or, no, okay, that's fine. All right. I will say, by the way, for physics students, there is a concept that you sometimes hear about called quantum field theory. That is actually a somewhat related concept. That's a concept where the function of position and time is a quantum mechanical operator. Okay, so instead of having a scalar that depends on position and time, or a vector that depends on position and time, those guys have a quantum mechanical operator that depends on position and time. So that's, you know, a related concept which some of you may come across in advanced quantum mechanics classes, but that is a little bit beyond the scope of what I'm talking about here. There are some interesting analogies, but I'm not going to talk about them here. So instead, what I want to do is to move on to a specific example where we might want to do calculations with a magnetic order parameter that depends on position. Okay, please, question.
Okay, I mean, in quantum mechanics, we mostly use psi, I mean, wave function, and if we are dealing with hydrogen model, then between at n is equal to 1 state, wave function is continuous, and at n is equal to 2 state, wave function is again continuous. But between two states, we cannot define wave function. Then how can we relate? Because in a classical mechanics, because we are basically dealing with quantinums, so velocity is continuous.
Yeah, there are different things in quantum mechanics, right? So one concept that many of you will have seen in quantum mechanics is a wave function. And so there's a wave function, which is a complex number that is a function of position and time. And that's one aspect of setting up the theory in quantum mechanics. There is a further aspect which you have seen, depending on how far you've gotten in quantum mechanics, which is where it's not just a wave function as a function of position and time, but there's also an operator as a function of position and time. So, you know, if you've studied the harmonic oscillator in quantum mechanics, you see raising and lowering operators. Okay? And so when people set up the analog of raising and lowering operators that depend on position and time, those are quantum mechanical fields. That's what people usually mean when they say quantum field theory. So that's the analogy that I was thinking of. But for now, let's not go there. Okay, so for now, let's just concentrate on the order parameter aspect. So if we're doing statistical mechanics, all right, if we're doing statistical mechanics, let's make up an example problem, okay, where the order parameter would depend on position. Okay, I'm just going to do position for now. I'm not going to talk about time, just position. So let's suppose that we have a non-uniform, okay, so non-uniform, not uniform, so not the same in every position. A non-uniform Ising magnet, and let's suppose we are in the disordered phase. So that means for a temperature T greater than the TC that we've been talking about so far this semester. So if it were a uniform Ising magnet, it would just be disordered, right? If it were uniform, it would just have M equals 0. But in this example, let's suppose that there is a wall somewhere. Okay. So here, I have a wall at x equals 0. Okay, and one property of this wall is that it forces the spins to point up. So along the wall, all the spins have to point up. Okay? Now, why would a wall do this? I don't know. Maybe the wall is like a localized applied magnetic field that is very strong. Okay? And it forces the spins to point up there, but it doesn't force the spins to point up far from the wall, right? Far from the wall, you'll have equal numbers of spins up and down because this is in the disordered phase, right? So far from the wall, we don't feel the effects of the wall. And because we're in the disordered phase, the spins will have equal numbers pointing up and pointing down. Okay, so that means that far from the wall, we have M equals 0, but right at the wall, we have M equals 1. In between, there must be some gradual change in the behavior. Okay? So in between, there must be some place over here where the spins are mostly up, but a little bit down. Mostly up. And then, you know, here, there's a little more up than down. And then over here, by the time you get very far from the wall, you have all this, you have equal numbers pointing up and down, right? And so the population is changing as you go from right at the wall to far from the wall. We could describe that mathematically by saying, you know, here is an axis x. Okay, so here is x equals 0, and then you go to large positive x over here. Large positive numbers. Over there, okay? And the magnetic order parameter has to be changing as a function of x. So it's a little bit like the cartoon that I was drawing for you before, where m is changing as a function of x. I can tell you a few vocabulary words to describe this kind of system. Okay, so one word for this that you might see sometimes is a semi-infinite system. Okay, so semi-infinite, that means half infinite. So that means it's infinite in the plus x direction, going off this way, but it's finite on this side, right? Because it has a wall that stops it at x equals 0. Okay? So it is blocked there. Infinite in one direction is called semi-infinite. Another word that you would hear is over here is called the bulk. Okay, so that means far from the interface or far from the wall. So the
I have a
bulk.
question.
Ibrahim,
Yeah.
sorry.
In the bulk,
Say it again.
In the bulk, we will take into consideration a degree of freedom of such particles or not. In this bulk, do you hear me?
Well, in the bulk, it's just like what we were studying before, right? So when we first talked about the magnet at the beginning of the semester, we said there are no boundaries, right? We just have something that a magnet that just continues on to infinity in all directions. Okay, so that was a bulk. Okay, and so we already know what happens in the bulk, right? We already know that the bulk has 0 magnetic order parameter for T greater than Tc, and it has some non-zero magnetic order parameter for T less than Tc. So this is the thing that you calculated in the first homework. Right? So that's the bulk order parameter. Now we want to figure out what is going to happen close to the wall and, in the whole transition region, going from the wall into the bulk. So we might make a plot of that. So we might say, let's make a plot for the magnetic order parameter as a function of x. Okay, so what's the trend for this order parameter field? Well, we know it has to be 1 right at the surface, at the wall. And we know it has to go asymptotically to 0 over here for large x. But the question is, how do you get from here to here? Okay. So it might just drop off really quickly. Like that. Or it might go really slowly. Or it might have some gradual trend like this, right? There could be all kinds of things like this, right? Or it might do something really crazy, like going like that, right? And so, these things are all possibilities. And suppose we want to figure out which of these things it does. Right? So what's our criterion, right? Well, the same as when we were studying before. We want to have the lowest possible free energy. Okay? So we have to ask the question, what field m of x gives the lowest free energy? Or in other words, we want to minimize the free energy over all possible fields M of X. Now, I'm hoping that you will notice that this is similar to the variational calculus that we've been talking about in the last few lectures, right? The idea in variational calculus is that we have a function of a function, functional, that is. That's what we have here, right? We have a free energy that depends on the function M of X. And we want to know what M of X function gives the minimum free energy, right? So we want to use the methods of variational calculus that I've been telling you about in the last few classes. Okay. So that means we need to write down what is the free energy in terms of M of X and then minimize it. Okay, so let's try to do that. So the first step has to be to express the free energy in terms of M of X. So to do that, I want to use Landau theory. Okay, so with Landau theory, this sort of symmetry-based theory, we would say that there is a local free energy density which depends on the local M of X. So that is this lowercase f, and we could express it the way that we talked about, I don't know, a week or two ago, as a power series in this local M of X. So we could say there's some 0th order term, F0, plus a quadratic term, so 1/2 A prime T minus TC times M of X squared plus 1/4 B0 M of X to the 4th power, right? This is the kind of thing that we were talking about for Landau theory, right? To say that the free energy must be some power series, and we have an argument that the odd terms must be 0 if there's no applied magnetic field. And then we could say there must be something else in the free energy which expresses the extra energy associated with spatial variations of the order parameter. So as I argued to you then, that could be written as some constant times the gradient of M, quantity squared. Now, this is the local free energy density. That is to say, the local free energy per volume. The total free energy is the integral of this local free energy density. Okay, so it's the integral over all positions of this local free energy, as a function of position, like that. So let's work with this. Okay, let's use this to try to set things up for a total free energy that is a functional of the function m of x. So we have a total free energy that is an integral over all three spatial coordinates. So an integral dx, dy, dz. Okay, that's what this integral d cubed r means in Cartesian coordinates, right? An integral over x and y and z. And then what we are integrating is f0 plus a half a prime t minus tc m squared plus a fourth v0 m to the fourth plus a half k grad m squared. Okay. Now, there are a few ways that we can simplify this. Okay? So one simplification is that we think m depends only on x. Right? And we would say that for a physical reason in this system, right? That we expect that m should depend on the distance away from the wall. But everything is the same in the y direction or the z direction out of the plane of this picture. And so we think nothing is going to depend on y or z. So if we say m depends on x, not y or z, okay? And then the gradient of m, now that is a vector, which is dm dx, partial m dx, partial x, and partial m partial y, and partial m partial z. But the y and z derivatives are both 0. All right, so this is just partial m partial x comma 0 comma 0. So that means that the magnitude squared of this thing is just dm dx squared. So that goes in here. Okay, that's one simplification. Okay. Now, another simplification is now when we look at the quantity that we're integrating, well, the first term is constant. It doesn't depend on anything. The second term depends only on x, not y and z. All these terms depend on x, but not on y and z. So the integral over y and the integral over z, those are both kind of trivial. right? That nothing depends on y or z. So it just gives us a factor of the system size in the y and z directions. Right? So what is left is a free energy, which is, whoops, not x, Ly, Lz, right? The system size in y, the system size in z, times an integral over x. Now, what's the range of x? Right? Well, it's a semi-infinite system. The system starts at x equals 0, and it goes up to x is infinity. Okay, so it's a definite integral from 0 to infinity of, f0 plus 1/2 a prime t minus tc m of x squared plus 1/4 b0 m of x to the 4th power plus 1/2 k dm dx squared. Now, I can make one more simplification that works because we are in the disordered phase. We're in the disordered phase. That is to say, m is small. M is much less than 1 almost everywhere. So because m is so small, that means we can neglect the m to the 4th term. The m to the 4th term is negligibly small compared to the m squared term almost everywhere. So that makes another helpful simplification for us. Okay, so the free energy in the end, well, it crosses off that term, okay, and what is left for us on pen is free energy, which is Ly Lz integral dx, and there's f0 plus 1/2 a prime t minus tc m of x squared plus 1/2 k dm dx squared. So this is now what we want to minimize. And we want to say, of all possible functions m of x, what gives the lowest value of this integral? This is a variational calculus problem to minimize it. Okay. And I will do so, but I'm out of time for now. So I will do so in 2 days. So you will stay in suspense for them. And I will come back to this in 2 days and actually do the minimization and see what is the best possible function m of x and how can we interpret that. All right, I will stop for now and I'll be glad to answer any questions, and then I'll see you guys on Friday. Thanks.